the energy we can store in a capacitor. So here's a very stupid animation of how a capacitor works. Okay? So let's say this is now a neutral capacitor, but neutral means same amount of positive and negative charge. Okay? So we start out, if this is a neutral capacitor, what's the voltage difference between the plates? 0. Okay? How much energy is there? Potential energy. Also 0. Okay? Voltage difference and potential energy are only different by Q. Alright? So, now let's say we attach this to a battery. That means charge starts moving. And you can see I moved the positive charge. That is not actually what happens. But thanks to the fact that we figured out electricity before we figured out what caused electricity, we've defined current as the movement of positive charges. And you can be angry at, I think Benjamin Franklin is at fault here. So, yeah, he's not going to care that you're mad and whatever. So this keeps happening, and eventually you end up with a situation that looks like this. Now you have a potential difference, right? You have a charge separation, which leads to a potential difference, which means you have potential energy, Q delta V. All right? This is what happens when you're charging a capacitor. Now, what you'll notice is the potential energy changes. We went from 0 to something, okay? So we have an increasing potential energy. And of course, just as a review, this is how work relates to potential energy, and this is our sort of semi-definition of capacitance, just rearranged, okay? So, if we want to calculate the potential energy, is V constant in this case? No, it went from 0 to something, so that is inherently not constant. V changes. Anytime we have change over time, we probably need to use some sort of derivative-y thing, okay, or an integral. So du v dq, okay, which means as you add more charge, you get more energy. Well, you can actually, this is not a hard integral, okay? So we're just going to go through it. We have du equals v dq. But what's v? Well, it looks like this, right? It's going to be q divided by c. All right? So that's going to be q over c dq. Right? Here's dq. Integrate both sides. We're getting kind of sloppy, but whatever. U, that's 1 over c. What's the integral of q dq?
d squared or q squared over 2?
Yeah, 1/2 q squared. Right? It's just a polynomial integral. So 1 over c, that's 1/2. So from 0 to big Q, right, the total charge. That's 1/2 q squared. That's it. So we end up with 1/2 q squared over c. This is our potential energy. All right? We don't have to derive this again, but that's what it looks like. You can also write it like this. And what have we done here? How do you go from here to here? Just plug this back in. Okay, q is just c delta v. So c squared delta v squared, you cancel a c. Same thing. Okay? You can always go back and forth. So, this is the energy stored in a capacitor. Where is this energy stored? Where do we store energy?
Batteries. Chemicals.
Where do we store the capacitor's energy? Not in the battery, right? It has to be somewhere in the capacitor.
In the capacitor.
We store it in the field.
Oh.
Okay? This is in the electric field. And this is kind of tricky, right? Because we're like, that's gravitational energy stored in the gravitational field. We store energy in fields, and we introduce fields as sort of this weird mathematical concept as a way to calculate force. But it turns out that fields store energy in their own right. They are a physical thing. They're kind of abstract. They're hard to understand, but they exist and they are a physical thing. The electromagnetic field stores energy. Okay? For instance, have you ever had a sunburn?
Yes, unfortunately.
That means an electromagnetic field burns you just once.
Just once. Yeah, me too.
And so
just once.
light
It
is an
sucks.
electromagnetic field, and it definitely carries energy, okay? Sunlight has energy, even though that's just a field floating through space or air in this case, okay? So you store energy in the electromagnetic field. Energy is stored in the field.
So this is a fairly important conceptual problem because remember, what determines the potential of a capacitor? So let's say we have a capacitor, and I'm just drawing sort of the cross-section of the capacitor. So the plates have area A, and they're separated by a distance d, and you know that one has a charge that's positive, so that would be plus q, and one has a charge that's negative, so that would be minus q. Okay? So when they're connected to a battery, the battery determines delta V. But if they're disconnected from a battery, so let's say we get rid of the battery, then when they're connected to a battery, the battery preserves delta V. So that means these can change, but this can't. When they're disconnected, that means the minus q and plus q can't change, but delta V can change. Okay? So we're going to think about a situation where these plates are moved apart. So we'll take this plate, and we're going to move it apart like this. And so now this distance is greater than d. So we have the disconnected case, and we have the connected case. In the connected case, you still have the battery determining delta V. In the disconnected case, you have plus q and minus q, but we don't know delta V. So let's go through our values of things we want to check if they can change or not. So for the case where the battery is still attached, we want to know what happens to Q, C, E, delta V, and U. And the same thing with where the battery is unattached. So we'll go through and do the things we know stay the same. So in the connected case, we know that no matter what we do, delta V has to stay the same. In the disconnected case, we know that the charge has to stay the same. And why does the charge have to stay the same? Well, there's nowhere for it to go. If you're over here in this case, the charge, when you move things apart like this, can come and go from the battery because the battery just stores charge and you can make it go either way. But if you have plates that are separated like these, then the charge can't just jump off the plate very easily, and so we're stuck with the charge that we had when we charged up the capacitor. The next stuff gets a little bit more complicated. So we know when the battery is disconnected that the charge stays the same. Well, what does that mean for the electric field? Well, we know the electric field for a parallel plate capacitor has to be Q over A epsilon naught. Well, has Q changed? No, we just said it can't. Has the area of the plates changed? No, just the distance between them. Has the material between the plates changed? No, it has not. So this is going to stay the same. All right. What about the capacitance? Well, the capacitance for a parallel plate capacitor, that we already calculated. That depends on the geometry, and that depends on epsilon or epsilon naught. So we know this is E naught, or just E, depending on the material, A over D. Well, E and A haven't changed, but D has. D got bigger. And if D got bigger, that means the capacitance got smaller. It's the same thing over here. If we know that this is EA over D, and D is the only thing really changing, because once again, if we move the plates apart, we don't change area and we don't change the material, then this gets smaller over here too. Okay, then we want to think about delta V. Now delta V does depend on D, and remember, delta V is ED for a parallel plate capacitor. So because of that, since we know that D got bigger and E stayed the same, so D gets bigger, E stays the same, this is going to have to get bigger. And if potential gets bigger, potential energy also gets bigger. You can look at the math, which for this case, the best thing to do would be 1/2 Q squared over C, where Q stays the same, but your denominator C gets bigger, smaller. So that leads to this being bigger. But you can also think about this as if you have a positive and negative charge, how do you store energy in that system? What do these charges want to do? Well, if you have a positive and a negative thing, they want to go towards each other. And if you're pulling them away, that means you have to do work. It's going to be hard to pull a positive and negatively charged thing apart. So you're storing potential energy in the field, and that means that potential energy should get bigger. Okay? So just to review, for this situation where the battery is disconnected, the charge has to stay the same, which means the electric field stays the same since we haven't changed the area. The capacitance has to get smaller because it depends on the distance, which is the only thing we did change, and the potential energy gets bigger. All right, let's go back over to where the battery is connected. So if the battery is connected, we know that only potential really stays the same. Oops. Because that's something that depends on the battery, and so the battery is going to adjust to keep the potential the same. And we know that the capacitance gets smaller. So if the potential stays the same and the capacitance gets smaller, what's going to happen to the charge? Well, remember, capacitance is Q over delta V. So if C gets smaller, but V stays the same, the only way for that to happen is for Q to get smaller. Well, what about the electric field? Well, the electric field, that's a little bit tricky. So let's go to the potential. The potential, electric potential stays the same. The electric potential energy has to change because we know that we have 1/2 CV squared, right? So this is equal to 1/2 CV squared. Well, V stays the same, but C gets smaller. So that means this has to get smaller. And this gets a little more complicated to think about. You're pulling these plates apart, so you're doing some work just to move these different charges apart, but the charges can move. And the charges, it turns out, go back into the battery. So that means even though you've pulled these charges apart, the plates are becoming less charged. So it should be relatively easy to pull them apart when they're connected to a battery because the battery is going to do some of the work. All right. The last but not least, we have the electric field. Now, what happens with the electric field? It's going to have to get smaller as well. And that's because we remember the electric field is charge divided by area over epsilon naught, or just epsilon if we're not in a vacuum. Well, charge has gotten smaller, but the area and the material haven't changed. So here's what we have. For the battery connected, everything gets smaller except for the potential, which stays the same by definition. When the battery is disconnected, the charge has to stay the same, And then some things get smaller, some things stay the same, and some things get bigger. We know how to add capacitors, yes?
Technically.
Technically.
We were given the information.
We practiced it. How do we add capacitors in parallel?
We just added
Add them up. So what's the same for every capacitor in parallel? Voltage. Yes, voltage is the same across each capacitor. Okay, it's determined usually by the battery, but even if there's no battery, voltage should be the same across capacitors in parallel. And you add up capacitors in parallel, C1 plus C2 plus C3. Okay, and what equation would we use to get charge knowing that information?
capacitance, time.
Yeah, this is the definition of capacitance, Q over delta V.
Capacitance times voltage.
Okay. How about in series? How do we add? What's the same on capacitors in series? Charge. Okay, charge is the same on capacitors in series. How do you add them up?
1 over
Inverse. Yeah, you add up the inverse. So 1 over C plus C1 plus 1 over C2 plus 1 over C3, and you'd have to invert the whole thing once you've summed it up.
So reverse for resistors.
Yes. They behave rather differently. Okay, so let's talk about energy density. So remember, we just derived energy for a capacitor. I know you guys all remember that. Looks something like this, okay? So we did some sort of integral. You guys were all really excited to use your integration skills, I remember. And this is the energy stored in a capacitor, okay? And remember, as you add more charge, you get more energy, right? So you add more charge to the plates, more energy is stored. And that should jive with what we know about potential energy. Okay, I'm sorry that my terminology is dated, very dated, even for me. I don't know, what's the... Mesh, there we go. It should mesh with what we know about potential energy. If you add more charge close together, you're storing more energy. And where is that energy stored? In the electric field. Energy gets stored in the fields, okay? So we're going to figure out a way to talk about energy density. So remember, energy, what was our formula for energy? Potential energy? Is 1/2 Q squared over C. Okay? So, energy density, let's talk about like just a parallel plate capacitor. All right? What's the capacitance of a parallel plate capacitor? We derived that, right?
Q over A over epsilon.
So remember C is like, what does it depend on? Area and distance. So I think it's epsilon naught over D. Okay, so let's plug that in. Get 1/2 Q squared, A epsilon naught, and then the D goes up here. Okay? Remember, what do we know about, I wanted to start with this. 1/2 is also equal to 1/2 C delta V squared. So let's use that one. 1/2 A epsilon naught over D. And what's V for a capacitor in terms of like electric field? Because what's the electric field inside a parallel plate capacitor? Constant. Okay, so it's E times what?
QC?
As you go across the capacitor, should the voltage be getting bigger?
Yes. No.
Depends on the direction.
Depends on the direction. Okay, so let's say you went from the negative to E times D, right? So E, electric field times the distance. So as you move across the capacitor, it goes up linearly, remember? So E D squared. Okay, so let's cancel some stuff. So this becomes 1/2. This is E squared D squared. So this becomes A D epsilon naught E squared. I want you to think about this. What's that?
Constant.
So this is the energy stored in a capacitor. What's A?
Area.
Area of what? The plate, right? The cross-sectional area of the plate. What's D?
The distance between the two plates.
Yeah, distance between the two plates. You have a parallel plate capacitor, you have this area, and then you have this distance. What does that represent? Volume. Volume between the plates, okay? A times D. So when we want to find density, let's say we want to find the volume density of energy, okay? So volume density of energy is this lowercase u. I know you can't tell that's a lowercase u. I know. That's going to be potential energy divided by volume. Does that make sense? Wait. This is volume density for energy, right? So charge density, charge divided by volume. Mass density, mass divided by volume.
So-
Energy density, energy divided by volume. So we take that, 1/2 volume, right? That's what AD is. Epsilon naught E squared. We divide that by volume, and we get 1/2 epsilon naught E squared. That is the energy density inside of a capacitor, okay? And we derived it for a parallel plate capacitor, but it turns out that works for all capacitors, okay? So what does this tell us about the energy density? What does it depend on? The electric field, which makes sense, right? Where is the energy stored? In the electric field. So the energy density depends on the electric field. And what does this tell us? The material, okay? So the energy density is going to depend on the material and the electric field, all right? So the energy density in any electric field is proportional to the square of the, in any electric field, yeah, it's proportional to the square of the magnitude of the electric field at any given point, okay? So if you know, this now obviously in other cases, this might not be a constant, but if you take this value at a point, it's always going to depend on the electric field, all right? Okay.